Let's chat integral test. Now, I should have added more constraints to this problem to make it work perfectly. Like right now, if a is equal to 0, then this isn't even a harmonic. And there are some situations where I could, like if I chose a equal to 1 and b equal to -1, then you can't even evaluate this series at the very first term because you'd have a 1 over 0. So let's just go clear that up really quick while we're here. Let's just say both a and b are greater than 0. If they're both positive numbers, that means that all of the potential discontinuities, vertical asymptotes, and the corresponding function would be with our negative numbers. And so on the domain that we're talking about, 1 to infinity, we would indeed be positive, continuous, and decreasing. Okay, now that that's out of the way, let's talk about what I was hoping to see and where y'all lost points on this particular question. So first and foremost, if we're going to use the integral test, typically we have to then write our corresponding function that we're going to use as our sort of replacement for the sequence, right? And then check that it's positive, continuous, and decreasing. I've told you can assume conditions are met, so we're able to just go straight to rewriting this in the corresponding integral form. So we're looking at area under the curve as opposed to these Riemann sums. One mistake here is that a lot of students just use the original argument for our series and did not put a dx here. It is okay if you left n, it's not great, but it's fine, right? As long as we had an n and then a dn, we're okay. So this alone typically netted you 1 point. If you had all of this just written down, I was like, okay, there's 1 out of 8. I really then wanted to see the limit as something approaches. In this case, we typically have been using b, but since I was annoying and had you do the general harmonic, b was off the table. You had to use some other variable to replace that with. I needed to see that you understood if we're talking improper integral, you know that we need to use that limit notation so that we can leverage the fundamental theorem of calculus. So now that we've gotten that, here's the next place a lot of students miss points. I really hope that we're comfortable doing the baby u sub that's about to happen. But if you were not, what was happening is students are going, okay, u is equal to ax plus b. du is then equal to a dx. And they were going, okay, so this is 1 over a integral, right? And this is where we have trouble because, right, our bounds need to match whatever our variable is that we have in our integrand and our differential, and this does not match, right? If you wanted to do that, you would have need to been like, okay, let me rewrite this. When x is equal to 1, this is an a plus b, and when x is equal to 1, well, or x is equal to t, this is an at plus b, and you still have your limit. Again, I think that that's just gnarly to work with, and typically I never want to encourage that sort of work on our questions, right? I just want to point out, if we're going to do u sub in the middle of an improper question, honestly, it makes sense to do our u sub off to the side, to do a little bit of floating math. So instead, we're going to do our floating math. We're going to just figure out what this antiderivative is. You could do that off to the side. Again, no need to do that. We should being the operative word, feel really comfortable, still need my limit notation, taking this antiderivative after all of our work in partial fraction decomposition land, that this is just going to be 1 over a ln of ax plus b. Cute, right? This makes sense. If we take the derivative, that ax plus b is going to be in a denominator, and we'd have to multiply by the derivative of that inside function there on our logarithm, which is just going to have an a. I need to evaluate this at t and 1. So one final step, and I'm fine with you skipping one of these two if you feel comfortable with it, but we end up with 1 over a ln of at plus b minus 1 over a ln of a plus b. Cool. Now we know if I were to evaluate this limit at as t approaches infinity, that we're going to get the ln of infinity, and we know that that is also infinite, so we might just want to write down, okay, that's infinity. So right now, we can write down that our integral diverges. So just to talk about places where folks lost points by now. One was having used b as your variable here. Because there was a b in the problem as well, that made things really, really sketch. Another was not keeping that limit notation on every step. Another was a lot of students did not remember or missed out on that 1 over a, and a lot of students did that u sub where technically they had incorrect bounds on their problem for a minute or overall if they actually evaluated that u with those new bounds. Didn't change the result. Nearly everyone came to the same conclusion that if we were to evaluate this improper integral, that it went off unbounded, right? That it approached infinity, so it diverged. Now here's the last thing I wanted to see. All of this work is so that we can say something about the OG series. So we're going to write down our OG series. I'm not going to write the series, even though it would be okay in this case because we only have one series running around. But this series diverges. So I've written the series again. I've given my conclusion, and I'm going to see what exactly I did to get that conclusion. Even though it's stated in the problem stem, you want your problem, your work to stand alone. So it diverges by the integral test. If you want to be really, really good, we've got our conclusion, we said the test we used, and you would have your because, blah, 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 but we're just going to say, hey, that's already been done. But a lot of students never ever said anything about why this diverges. They just wrote down this piece right here that we had something equal to infinity, and then just wrote down, hey, this thing diverges. And I don't know if you're talking about the original integral. I don't know if you're talking about the series. Even if you did write the series, not telling me that you did this, all that work up above had a purpose, right? Because it's all about your communication in this section that we're in here with series. So this was what I was looking for, and those were some of the common mistakes for problem 4.